Before we go further, let's just take a step back and say that when Google searches based on your inquiry, there's actually quite a bit of work going behind the scene. First of all, Google need to constantly crawl the web so that it can keep track of all the new web pages and the changes on the existing web pages. Then it need to store the information collected about these pages and index them in a database. And then it would need to compute, in fact, 2 rather than just 1 scores, and then rank the pages and then display them for each search. 1 score is what we were talking about, the importance score, and that will be the sole focus in today's lecture. But there is also a relevance score. Okay. It has to make sure that it doesn't just rank all the 60 billion pages out there for every inquiry. You only rank those that are relevant. Now, this is an important topic in information retrieval, in database management. We just won't have time to talk about it. But we know that for any reasonably popular search terms, there will be many relevant web pages. And then what matters in deciding which web page will show up on page 1 of the search result often boils down to the difference in the importance score of this, eventually a composite of 2 scores. So it is the importance score determined by the connectivity pattern of the web page graph that will often determine the final ranking of the top, say, 10 or 50 or so web pages. And before we can go further, we also need to talk a little bit about a notation and operation of linear algebra objects. Now, I know that some of you may not have taken linear algebra. Some of you may have forgotten about it. In 2013 May, we will have a summer course, a version for this very course, where we will have no need for any linear algebra terminology. It is possible to talk about everything we are going to talk about without using the language of linear algebra. However, that discussion will take a much longer time, because without these shorthand notations we call vector and matrices, it would be very hard to explain every step. And a lot of the existing results from linear algebra concerning matrices we won't be able to use. So in the interest of time, we will have to then shrink the discussion to a much smaller subset of what we will be talking about in this course. So I just want to highlight that it is possible to talk about these things without the machinery of linear algebra, which we will indeed be doing in May 2013. But in this version of the course, we will be using linear algebra. Okay. It is a very useful shorthand notation plus a powerful set of machinery that will allow us to accelerate the discussion. Now, I'll try to make this as non-linear algebraic as possible, but at some point we will have to do a little bit of that kind of math. Okay, so if you need to tune out, feel free, but you may still be able to get some of the interesting ideas, even though some mathematical operations may be beyond your understanding at this point. All right. So we have been using vector quite a lot, right? This vector pi is a vector, and by convention, a vector is a stacked up column. Okay, pi 1, pi 2, pi n, say pi 100. Okay? And what's a matrix? Well, a matrix is really, in general, an object with, say, n rows and m columns. Okay? So we can think of that as many vectors arranged in parallel, or we can think of that as many rows stacked up. Okay, either way. Let's say we got a matrix A, then we can denote this matrix A's ijth entry as A sub ij. Okay. In all of the material that we would be talking about, this is just a real number. Could be positive, could be negative. In today's lecture, it is never negative. And sometimes we use a little arrow on top of a big letter to represent that it is a matrix. A matrix multiplying a vector is a funny operation, you may say. Say, if matrix A multiplies a vector x, let's say matrix A is 2 by 2. Say it is 1, 3, 4, 2. Okay. And vector x is just x1, x2. What you get is the following. Okay. First of all, the matrix is 2 by 2. The vector is 2 by 1. So what you get is a 2 by 1 vector. The first entry is the inner product of the first row vector of the matrix and this vector x. So that is x1 plus 3 times x2. 1 times x1, 3 times x2. The second entry of the vector is the second row of matrix A times the same vector x. So we have 4 times x1 plus 2 times x2. Okay, so this is the basics of matrix multiplication. Now somehow in this lecture only, because of the research community's convention of writing these quantities, they actually, instead of writing a matrix multiplying a vector, they write it as a vector multiplied by a matrix. Now you may say this doesn't even make sense because the vector is, let's say, 2 by 1. The matrix is 2 by 2. You can't multiply 2 by 1 on the right by 2 by 2. Indeed, that's true. So what we need to do is to flip this vector into a row vector. For example, in this case, it will be x1, x2. This is a 1 by 2 row vector times the matrix, which is 1, 3, 4, 2. That's matrix A. Then it's okay, because X transpose with this big T on top is flipping the column vector into a row vector. And now you have 1 by 2 object times 2 by 2 object. And that makes sense because this is 2 and this is 2. The dimensionalities actually match. So in today's lecture, we'll be multiplying the vector pi on the right. So we have to write as pi transpose multiplied by different matrices on the right. Okay. This is just an perhaps unfortunate convention of the notation in this specific research community. So we talked about matrix multiplication, right? And now think about the following. Suppose I got a vector pi here and make it transpose. So it is a row vector and multiplied on the right by some matrix A. Suppose after being multiplied by this matrix A, what you get is actually some constant, let's say half, times the same row vector, pi transpose. Then, in that case, we say this vector, pi transpose, is an eigen vector, means that it maps back to itself corresponding to this matrix A. Okay. It might be a scaled version of itself. Every entry in the vector is scaled by some number. Okay. And this scaling factor is called the corresponding eigenvalue. In today's lecture, we'll be constructing 3 different matrices. Start from the simplest one based on our current intuition and then point out why that doesn't suffice. And then suggest an enhancement. That's why we're going to go through a sequence of 3 matrices. And the final product is a matrix, what we call the Google matrix G, that captures the connectivity pattern of these web pages on the web. And we'll see that this matrix G is the so-called non-negative matrix, meaning that each entry in G sub ij, the ith row and jth column entry of this matrix G, for all the i's and all the j's, meaning every entry in this matrix G must be a non-negative number. It could be 0, but can be negative. And it turns out that there's a whole branch of mathematics in linear algebra that studies non-negative matrices with many properties. Okay, that's often called Perron-Frobenius theory of non-negative matrices. One of these results says that there will be a largest eigenvalue which is exactly 1. In other words, we can find an eigenvector associated with this eigenvalue for a given matrix, say A, such that pi transpose multiplied on the right by A returns nothing but the same vector pi transpose. Well, you can also write down this 1 in front of it. It's okay. That is the eigenvalue. Now you may say, why are we even going through all these matrix multiplication and eigenvector and eigenvalues for non-negative matrices? What has this got to do with Google's web page ranking? As we will see in the next 30 minutes or so, that the ranking is determined by the importance score vector pi, and pi really is nothing but the eigenvector associated with eigenvalue of 1 of a matrix, this Google matrix. Okay, instead of writing a generic matrix A, let's write down the Google matrix G. In other words, we will go through a sequence of steps to properly define matrix G such that the ranking, importance score, pi vector can be computed as the dominant eigenvector, the eigenvector associated with the largest eigenvalue, which happens to be 1, of this matrix G. And from this pi, we can then compute, we can then order the web pages to be displayed. So that's the game plan for the rest of the lecture. And then we start with nothing but our same small example. Nodes 1, 2, 3, 4 with 6 directed links. Now we already know the answer, but we're going to now derive that answer using a matrix notation. And in the rest of this course, we will see quite a few other matrices, especially around lecture 8. All right, so the very first matrix we'll construct to represent this graph is a matrix denoted by H. Before we define the ijth entry of a generic matrix H for any general hyperlinked web page graph, let's just look at this specific example. I'm going to define the corresponding matrix H, which is 4 by 4, because there are 4 nodes, as the following. Look at node number 1. That will give me the first row of this matrix. Number 1 is pointing to number 3 and no one else. So I want to capture that information. So 1 doesn't point to back to self, 1 does not point to node number 2. Let me just label these columns and rows. But it does point to node number 3. It does not point to node number 4. See, just by writing down zeros and ones in this row, I am encoding, representing the graph, at least part of the graph. Okay, what happens with node 1's outgoing links? Now, you may remember we also want to normalize by the number of outgoing links. Well, it's actually already captured here. There's only one non-zero entry here, so the number of outgoing links is 1. Now, we could write 1 divided by 1, which is 1. Okay, that's fine. What about node number 2? By symmetry, it's actually the same as node number 1. So 0, 0, 1 over 1, 0. This 1 is an indicator to indicate that, hey, there is a link from node 2 to node 3. This 1 is a counting variable. It says, I count there is only one link coming out of node 2, pointing to some other node. So actually the function of this 1 is not the same as the 1 in the denominator. What about node number 3? Well, it only points to 4, so you know the answer, 0, 0, 0, and then 1. Divide by 1. What about node number 4? Now, this gets more interesting. 4 points to all the other 3 nodes except itself, so this is 0. So you can see the diagonal of this matrix 0 because no node points back to itself, but points to everyone else for node 4. So we have to write down 1, 1, 1. Now, we can just write it as such, but to make the computation easier to carry out, we're going to incorporate this normalization right within the definition of this matrix H. We say, since there are 3 outgoing links, let's represent the normalization by dividing each entry with 3. So we got 1 over 3, 1 over 3, 1 over 3. Now, you can see immediately that every row of this matrix H sum up to 1. Okay, well, that's by definition, by design of this matrix H. We constructed such that it sum up to 1, unless this node points to no other web pages. We'll come back to that in the next module of the lecture video. Okay, for this graph, we are fine. Okay, so you may have a lot of zeros, which is actually the real case because the real web is very sparse. And then you have non-zero entries, which are actually identical. They are basically all just 1 divided by the number of outgoing links. And then, of course, obviously, they'll sum up to 1 per row. This is how we construct this matrix H. You say, what's the point? I mean, I can see you are capturing the connectivity pattern of the graph algebraically in a bunch of numbers in a matrix. But why? Why would you want to do that? Well, because this will facilitate, accelerate our discussion. For example, now when I say I want to write down the relationship of these nodes' importance scores, for example, okay, pi 3 equals pi 1 plus pi 2 plus pi 4. Okay, over 3, because pi 4 is split across 3 ways. I can write this down by staring at the graph. But of course, when the graph becomes big, for a computer to stare at it is actually staring at an algebraic representation of the graph. Okay, that gives you everything you need to know about the graph. And as you can see, what's happening is the following. Just look at this column, not the row. I know we constructed the graph row by row, but now look at each column. It says that pi 3 really is pi 1 plus pi 2 plus pi 4 times 1 over 3. In other words, if I give you a row vector, pi 1, pi 2, pi 3, pi 4, and I ask you to multiply with the third column of this matrix, which is 1, 1, 0, 1 over 3. This is what you get. Right? Pi 1 plus pi 2 plus pi 4 over 3. Aha! If that's the case, then actually, in order to compute these pi's, all I need to do is to multiply this row vector on the right by the corresponding column of this matrix H. So in general, what we can do is to say pi vector transpose times H matrix will give me the new pi. Okay. And what is this h in general? In general, this h is defined as the ijth entry. Could be 0. Okay, if I does not point to node j. But if I does point to node j, it is nothing but 1, well, normalized by the out degree of node I. That's the general definition of matrix H, which you can check is exactly what you got from this numerical example. So generally, you can define the ijth entry of matrix H as such. What's the point of doing that? The point is that then you can represent the linear equation through a matrix representation. Pi transpose times H equals pi transpose. Because of the manual observation, writing down this equation based on our try-to intuition is now entirely captured in this representation of multiplying pi transpose on the right by matrix H. Okay. Because we're multiplying this row vector by the jth column of matrix H to get pi j. All right. So now you say, hey, we're done. Well, there are two issues. A, it turns out that this matrix H doesn't always give you the existence of a pi that can satisfy pi transpose H equals pi transpose. And that's problem number 1, and we're going to tackle this in the next 2 modules of the video. Problem number 2 is that what about the computational load, even if for a certain graph this H suffices? What's the computational load to compute the eigenvector of a matrix, say H? If you use MATLAB or C or whatever language you use, you say, hey, that's not too bad. Okay. That's assuming H is not too big. But if H, it doesn't even have to be 60 billion by 60 billion. If H is, let's say, 100,000 by 100,000, 100,000 relevant web pages to a popular search term, then computing the eigenvalue is a very intensive job. So Google need to do this real fast. How can we do that? It turns out that you can do it in an iterative fashion. Now, back in lecture 1, when we talk about distributed power control, it was an iterative algorithm too. But it was iterative back then because no one has a global view of the network condition, of the direct and interference channel gains. In this case, lecture 3 now, we also use iterative algorithm in Google's web page ranking method, but this time it's because the computational load would be otherwise too big. And back in lecture 1, we not only used iterative but also distributed. That's why there's a letter D here, because we cannot afford a centralized computation. In this case, however, we can afford a centralized computation. So both DPC and Google's ranking algorithm are iterative algorithms, but one is distributed computation, the other is centralized computation. Now, towards the end of the 4th module of this lecture, we will come back to this iterative method. You're going to compute the pi, not directly by computing the eigenvector of matrix H. But instead, you will keep multiplying pi transpose on the right by H. Call this the first iteration. Then that gives you pi transpose the second iteration. Now substitute this pi back here, then you get the 3rd iteration, 4th iteration, and so on and so forth. Now matrix multiplication is not a simple job computationally speaking either, but at least this is each step of this iteration is much lighter load than computing directly the eigenvector. And if this can converge quite fast, then we have a computationally efficient way for Google to compute pi and thereby rank the web pages. So now we have two issues at hand. One is that this matrix H captures most of our intuition, but not quite. Turns out we need two modifications to ensure the existence of pi. Second, we need to efficiently compute when such a pi exists. So the rest of this lecture, we will focus on these two issues until we get to the point where there's matrix G, the Google matrix, that leads to a guaranteed existence of pi and efficient computation of pi through this iterative method.